These are your instructions. In general, you just need to follow a PowerPoint. Please make sure the sound is turned up on your device so you can hear the narration. On some of the slides, there are instructions for you in the yellow boxes. And don't forget, if a slide asks you for homework, send it in via Show My Homework. And if a slide asks for Educate to be completed, don't forget to do it by the date given.
At the end of this lesson, you should be able to describe the energy changes taking place when a vehicle brakes and also describe the potential dangers of a large deceleration. Let's start by recalling our diagram of how stopping distance varies with speed. The first point is, I hope, quite obvious. The faster you are going, the larger your stopping distance is. If you remember, we divided our total stopping distance into two sections. We had a thinking distance, which is the distance you cover while you're reacting to an obstacle, and the braking distance, which is the distance that the vehicle covers once you've actually pressed the brake pedal down. Now, at each speed, your stopping distance is the total of your thinking distance plus your braking distance. I want to look at the thinking distance and the braking distance separately. So first of all, let's have a look at the thinking distance. Now you can see that as your speed increases, your thinking distance increases, but it doesn't increase by a great deal. Now this is because your reaction time is about the same whether you're traveling at 30 miles an hour, 50 miles an hour, or 70 miles an hour. So let's say it takes you about half a second to react. As your speed increases, the distance the car covers while you're reacting will increase by a small amount. The other part of your stopping distance is your braking distance. And if you look at the diagram, you can see that as your speed increases, your braking distance doesn't increase by a small amount each time. It goes up by a large amount each time. Now this is because of the forces and energy transfers involved while you're braking, and it's those that we're going to look at today. Let's start by recalling our work on kinetic energy from the energy topic. You should remember that every object that is moving has kinetic energy. And you should remember that there's a formula for working out the amount of kinetic energy. And it looks like this. The kinetic energy is equal to a half mv squared. So that's the kinetic energy in joules, can be calculated by multiplying a half times the mass in kilograms times the velocity times the velocity. Let's have a look at a vehicle and see if we can work out how the kinetic energy varies as the speed increases. So, we know that the kinetic energy can be calculated using a half mass times velocity squared. So let's have an example. So we have a car of mass 1000 kilograms traveling at 20 meters per second. Let's work out its kinetic energy. Using that formula, substitute in your figures. Kinetic energy is a half times the mass, which is 1000, times the velocity, which is 20 squared. Now, if you work that out on your calculator, the energy comes out at 200,000 joules. Now, if we take the same car and double the velocity to 40 meters per second, and do the same calculation again, so it's a half times 1000 times 40 squared this time, the answer comes out to 800,000 joules. So we've doubled the speed, but the kinetic energy hasn't doubled. The kinetic energy has quadrupled because of that v squared term. Now, the vehicle has kinetic energy, and if we double the velocity of the car, the kinetic energy quadruples. In order to stop the car using the brakes, all of that kinetic energy has to be converted to other forms of energy. You remember, energy cannot be created or destroyed. So all of that kinetic energy from when the vehicle is moving has to be dissipated some way because the kinetic energy will be zero when the vehicle has stopped. So all of that energy has to be converted into other forms of energy. Now, this is the main energy transfer that happens when a car's brakes are applied. There's lots of different braking systems, but they all work by friction. So if you have a look at this diagram, you can see a foot being depressed, and that causes further along for a pad or a disc to be pressed against the rotating wheel, and that's what slows it down. So when the brake pedal is pressed, brake pads are pushed against the wheel and slow it down. The force of friction is the force that acts between the pad and the wheel to cause it to slow down. In terms of energy, the kinetic energy of the car is converted into thermal energy in the brakes. Now this causes the brakes to heat up and the car slows down as it loses kinetic energy. Now, the faster the vehicle is traveling, the more kinetic energy there is to transfer. This means that the greater the speed, the greater the braking force you need to stop the car in a certain distance. Or another way of looking at it is if a car is traveling at high speed, the driver will need to apply a large braking force. There are some dangers involved in applying such a large force. If you look at these diagrams, you can see a large braking force will cause the car to decelerate rapidly. That means it slows down rapidly. But this can cause a few problems. Because a large amount of kinetic energy is transferred to thermal energy in the brakes, they can overheat. This makes them less effective. Also, if you apply a large braking force, you can cause the vehicle to skid and lose control. Now we know from our work on energy that another way of saying that energy is transferred is to say that work has been done. So in this case, we could say that energy has been transferred away from the kinetic energy store of the car, or we could say that work has been done to stop the car. The faster the car is traveling, the more work that has to be done to stop it. And we can write this like this. The energy, kinetic energy, is a half mv squared, is equivalent to the work done by the brakes in stopping the car. And we know a formula for the work done, force times distance. So these two can be made equivalent to each other. Let's see if we can apply some of this knowledge to answer an exam question. This is a 9-mark question, so it's quite a long question. I've divided it up over 4 slides and I've put the answers on the in-between slides so you can green pen your work. Have a go at it now for me. final task from this lesson is to send me a picture of your work from this lesson via Show My Homework by Friday the 10th.